Today we are going to talk about bipolar junction transistors. For BJTs. So the first thing that I want to talk about is the device structure and the operational modes. So in reality, a BJT, what the hell just happened? There we go. Structure is going to look something like this. So let's say that we have a substrate. And this is going to be N-type material. And then over here, let's have a separate substrate. And this will be P-type material. And then we're going to have what's called a well. Inside of our substrate, like so. And in this case, this is going to be P plus, where the plus sign means that it is more heavily doped P-type than the substrate was doped N-type. And then similarly over here, we're going to have an N plus region. And then we are going to have an implant here that will be N plus plus. And we'll have an implant over here that'll be P plus plus. So this guy on the left is what's called an NPN BJT. And this guy over here on the right is what's called a PNP BJT, where the heavily doped portion of the crystal is the emitter. The medium doped portion is the base. And then the lightly doped portion is the collector. And that is true for both NPN and PNP BJTs. So emitter, base, and collector. So this is what the cross-sectional area of a bipolar junction transistor is going to look like. But much like we did with PN junctions, this isn't actually the model that we're going to use to kind of understand what's going on inside of these things. Instead, we are going to use kind of a sandwich model. I know that sounds a little bit weird, but effectively, if we drew a line down through this guy, we would see a heavily doped region of one particular type, and then a slightly less heavily doped region of the opposite type, and then a very lightly doped region of the opposite type yet again, so that we would have something like this. So we might have this is going to be our neutral N region, commonly called the collector. Our neutral P plus region, commonly called the base. And our neutral N plus plus region, commonly called the emitter. For the PNP BJTs, it's going to be the same type of thing except flipped upside down, and we'll talk about that here in just a moment. So here we're going to have the neutral P plus plus region, which is our emitter. The neutral N plus region, which is our base. And the neutral P region, which is our collector. And I'm going to go ahead and throw some terminals on these guys. So this is our collector terminal, our base terminal, and our emitter. Here we have emitter, base, and collector. And I've drawn them in this way, where the expected point of highest electrical potential is on top, and the lowest point of electrical potential within the device is on bottom. So we can see that for an NPN BJT, the collector is typically at the highest point of electric potential, at least when it's used for amplification purposes, which is what we're going to be focusing mainly on in this class. Whereas for a PNP BJT, the emitter is usually at the highest point of electrical potential. So this is going to have some bearing on the direction of currents that flow through these devices as well. And we'll talk about that in more detail when we get into the physics. But for now, let's say that our collector current IC is going to be flowing into the device. Our, base current IB is going to be flowing into the device, and our emitter current IE is going to be flowing out of the device for an NPN BJT. And then for a PNP BJT, it's literally the opposite. Our emitter current flows in, our base current flows out, and our collector current flows out. And then because it would be a pain to do circuit analysis using this particular model, I'm going to give you the schematic diagrams as well. So for a NPN BJT, we're going to have our collector on top, our emitter on bottom, and then our base here in the middle. And this is an arrow indicating that our emitter current is flowing out of the device. Okay. Important voltages for us are going to be the base emitter voltage, VBE, the collector base voltage, VCB, and the collector emitter voltage, VCE. And then while I'm at it, I'm going to throw on here IC, IE, and IB. And then over here, I'm going to give the same treatment to our PNP BJTs. So here is our emitter. We have an arrow indicating the emitter current is flowing in. And then once again, here is IB, IE, and IC. And then we're going to have the exact same voltages as we had on the NPN BJT, except that the subscripts are going to be flipped. So instead of having VCE, we'll have VEC. This will be our voltage VEB, and this will be our voltage VBC. So just to recap here, this is what the physical structure actually looks like, where we have a very lightly doped substrate, and then we put in a more heavily doped well, and then inside of that well, we put in an extremely heavily doped implant in order to get our N-type, P-type, N-type, or vice versa, PNP over here. Then we have our sandwich model that we're going to look at. So this interface right here is what's known as the base collector junction. This interface right here is the base emitter junction, and how these PN junctions are biased, whether they're forward biased or reverse biased, is going to tell us a lot about how the device operates. And then the same thing on this side, except that the position of the base emitter junction and the base collector junction are flipped, because we want the highest potential to be the emitter for the PNP BJT. All right, so let's talk about why things are the way they are. All right, so the doping concentrations of each of the three regions is critically important to the device operation. So that we need the doping concentration of the emitter to be higher than that of the base, which is higher than that of the collector. Okay, so the emitter region of the device is very heavily doped because this region supplies the principal charge carriers for current conduction. So effectively, we want our emitter to be as doped as we can possibly get it, so that we have as many free charge carriers available so that we can pass a large amount of current through the device. The base region is doped less heavily than the emitter, and is used to control the flow of charge carriers as they travel from the emitter to the collector. So effectively, what we have is a voltage controlled current source, right? The larger our base emitter voltage is, and let's put absolute value here, base emitter voltage, that way it works for both NPN and PNP BJTs. The larger that base emitter voltage is, the more current we're going to see flow through the device. So there is proportionality directly between our base emitter voltage and the overall current flowing through our device. So one of the models that we're going to use to look at this thing is actually a voltage controlled current source model. Okay. One other thing to know about the base is that the base region is very thin. And it is thin to prevent excessive recombination in this region. So let's talk about this very briefly, right? So if we had a generic PN junction where both sides are long, what we saw is that our minority carrier concentrations tended to exponentially decay down to the equilibrium levels, right? We don't want that to happen in the base. We want the minority carrier levels to be high so that we get large amounts of current flowing through our device. So we actually need our base region to be as thin as we can possibly make it. This is an interview question that I got asked a couple of different times from companies about why you can't make a BJT literally by just putting two diodes back to back, because that's really all a BJT is, electrically speaking. And the answer is because if you put two diodes back to back where the regions are large, you will not get the charge control that you're looking for here, because you need recombination to not occur effectively, or significant recombination to not occur, so that you have free charge carrier available for conduction. So it is critical to the device's operation that the base is actually the physically smallest part of the device. Okay. Lastly, we have our collector region. So the collector region is lightly doped in comparison to the base, so that reverse bias of the base collector junction forms a large electric field which sweep diffusing carriers from the emitter through to the collector. Again, we'll describe all three of these things in a little bit more detail when we're looking at the physics specifically. All right. So this is our device structure and a little bit of detail about what each of the three regions do. Now we're going to talk about the different operational modes very briefly. Okay. So BJTs can operate in one of 4 different modes, depending on how the different junctions are biased. So I'm going to write here a little table. So we're going to have mode, and then the state of the base emitter junction, and then the state of the base collector junction. So if the base emitter junction is reverse biased and the base collector junction is reverse biased, then we are in what's called cutoff mode. So cutoff mode effectively means that no current is flowing through the device, so the transistor as a switch is effectively off, okay? So hopefully this should make sense. If both of our junctions are reverse biased, there's really not any opportunity for any charge carrier diffusion to occur, or the probability of charge carrier diffusion occurring in either direction is effectively negligible, right? If both of them are forward biased, then our device is operating in the saturation mode of operation, okay? And cutoff and saturation are the 2 modes that are typically associated with using a BJT as a switch or in digital circuits, right? So we have an off state and an on state, and literally nothing else matters. Now, if the base emitter junction is forward biased and the base collector junction is reverse biased, we have what's called the forward active mode of operation. Forward active mode is what's used in BJT amplification applications, which is where we're going to spend most of our time talking about. And then if the base emitter junction is reverse biased and the base collector junction is forward biased, we have the reverse active mode of operation. And the reverse active mode of operation behaves very, very similarly to the forward active mode of operation, except that the junctions are biased the opposite direction, which means effectively we're trying to get charge carriers to diffuse and travel from the collector to the emitter. So from a region where there are very few charge carriers to a region where there are a whole bunch of charge carriers. So effectively it's going to work, but we're going to get either very, very low currents, or if we get very high currents, it's because we have extraordinarily high temperatures that are causing that to happen. So realistically, we never actually operate the device in reverse active region on purpose. It will behave as if it is in the forward active region. It just gets really, really hot doing so because it needs that extra energy in order to have enough charge carriers pass through things. So these are our different operational modes, and we're not really going to talk about cutoff anymore because it's just everything is off. There's no current flowing anywhere. It's very boring. We're going to talk about saturation a bit later. We're going to cover forward active today. And then, like I said, reverse active is never intentionally used. So we're really not going to talk about that one either. All right. So because the picture I want to draw is large, I'm going to go ahead and go to another page here. All right, so I'm going to draw our sandwich model here, and I'm going to draw it rather large so that we can see what's going on. because we're focusing on an NPN BJT, this top region is going to be our collector, which we know is doped N type. So that's what that little N in the top right corner is. It's just reminding me of what the dopant is. Here's my base region, which is P plus. And then here's my emitter region, which is N plus plus. And so I'm going to put a voltage source between the collector and the base. Like so. So let's call this VCB. And I'm going to put a voltage source between the base and the emitter. And this will be VBE. This is my base emitter junction. And this is my base collector junction. All right, so another couple of things. Actually, we'll talk about this here in a moment. All right, so for our BJT to be in the forward active region, we need the base emitter junction to be forward biased, which means the voltage VBE must be greater than or less than 0. Which one? So we want this base emitter junction to be forward biased. This is the P side of the junction. This is the N side of the junction. The positive polarity terminal of this voltage source is on the P side. The negative polarity terminal is on the N side. Does this voltage need to be positive or negative for this PN junction to be forward biased?
Positive.
Positive. Okay. So VBE needs to be greater than 0 for that junction to be forward biased. We also need the base collector junction to be reverse biased. So here we have the positive polarity terminal on the N side, the negative polarity terminal on the P side. VCB should be positive or negative? Negative. Absolutely right. Or actually, so VCB should be positive in order to make this guy reverse bias, right? So both of these voltages need to be greater than 0. Another way to think about this is that the collector emitter voltage, VCE, must be greater than the base emitter voltage, VBE, in order for us to be in the forward active region, right? So hopefully this makes sense. This is a quick aside thing here. So VCE is minus VE, which could be expressed as VC, dang, I'm gonna keep doing this, VC minus VB plus VB minus VE is VCB plus VBE, just going through things here, right? So VCE will always be greater than VBE in a forward active because we know that both of these voltages are positive quantities. All right, so these biasing conditions mean that the barrier potential across the base emitter junction is lowered which is going to yield a small electric field in the up direction. So this side is very heavily doped, so I'm going to draw the width of the depletion region very thin. And then this side, the P side, is more lightly doped, so this side's going to be wider. So we have here bound positive charge, and here bound negative charge. Actually, I got that backwards. So we should see a small electric field in the up direction, right? So this area is devoid of holes, so it's leaving behind a negative bound charge. This area is devoid of electrons, so it's leaving behind a bound positive charge. Our electric field should be directed from the positive charge to the negative charge. And then looking at the base collector junction, we're going to see something similar. Here we have bound negative charge. Up here, we have bound positive charge. Because we're going to have more charge, we are going to see a stronger field in the down direction. And this is a direct consequence of the biasing of our junctions, right? So because our barrier potential is lowered, we get a small electric field. Because our barrier potential is increased, we get a large electric field here. All right. So the reduction in barrier potential for the base emitter junction means that electrons from the emitter can diffuse into the base region. Okay. So I believe I've been using blue for electrons. So we're going to have something like this. So this is a big, broad, wide arrow. It's telling us electrons are diffusing from the collector, from the emitter into the base. Let me label things here so I don't screw that up again. And similarly, we should see that holes are able to diffuse from the base into the emitter. Because our base is more lightly doped, we don't expect to see as many holes diffusing. The carrier diffusion across the base emitter junction is going to yield a current flowing out of the emitter terminal, i.e., like so. And for an NPN BJT, this current is dominated by the electron diffusion. So we should see that this current IE is predominantly caused by this electron diffusion. And when we start throwing math at this thing, we're going to see that we're dealing with electron diffusion probability. Okay. All right. So these electrons here are in this very thin base region, and they are going to diffuse towards the collector. Why? The collector is very lightly doped n-type, which means that as long as we don't allow too many of these diffusing electrons to recombine, it's still going to see a concentration gradient that will enable diffusion into the collector region as well. So we're going to see something like this. So I'm going to draw my arrow like so. So this is still electrons. And I'm drawing this one not quite as wide because there will be some recombination. So the current that we see flowing through the collector is going to be slightly smaller than our emitter current because of the recombination that occurs in the base. Because electrons are moving up, positive conventional current will be flowing down. So this is where IC comes from. Our collector current IC. So we have these electrons that are diffusing. They see this very large electric field, and they see a region of low electron concentration. And so they get swept through, much like we saw current in a reverse bias PN junction, because that is exactly what we have here, a reverse bias PN junction, except that we have a whole hell of a lot more charge carriers available, okay? So mathematically, we should expect to see something that looks like the reverse bias saturation current of a PN junction. So our collector current IC is given by the following relationship. So this is AE, which is the cross-sectional area of the base emitter junction, and I'll write that down in a moment, times Q, charge of an electron, proton, whatever, dN, our diffusion coefficient, Ni squared, so our intrinsic carrier concentration, divided by Nb, which is the dopant concentration of the base, Wb, which is the effective width of the base, times exp of VBE over VT, where this term right here is the saturation current for our BJT. Now I'm going to note out here, AE is the area of the base emitter junction. NB is the dopant concentration of the base. And WB is the effective width of the base. One thing that I want to point out, and this is a little bit of a problem with our model that we'll address here in the next day or so, is that at present, our collector current only depends on the voltage applied to our base emitter junction. So effectively, we're saying everything is related to the probability of diffusion from here to here, and the voltage applied across our collector base junction doesn't matter. Why isn't that going to be really true? So BCB, what do you mean affects the recombination rate?
Like the voltage with that size
You've nailed it. Okay, so North has absolutely nailed it. Okay. So the size of these depletion regions is dependent on the voltage that is applied, right? So as VBE gets larger and all of this kind of stuff, this depletion region is going to get smaller and smaller, right? As VBC gets larger and larger, this depletion region is going to get wider and wider, which is going to wind up actually making the width of the base appear to be smaller. And as the width of the base changes, we should see that our collector current increases, right? So VCE or VCB or VCE, either way we choose to look at it, is going to have some impact on the collector current. And that's called the early effect, which again, we'll talk about in much more detail here in a couple of days. But for now, we're going to deal with this, and then we'll add in the second order effects in a little bit. Okay, great job, North. All right, so let's see, I've identified my collector current, my emitter current. We've talked about electron diffusion from the emitter into the base. They get swept through from the base to the collector. So now let's talk about what's going on with the base in particular. All right, so the base terminal of the device supplies holes to the base region to sustain the hole diffusion into the emitter region. So because we have some base current IB, like so, that is a positive or conventional current, we should see that our base terminal is responsible for effectively supplying the holes or replenishing the holes that diffuse into the emitter, as well as providing holes to recombine with the electrons as they diffuse across the base. The base current is typically defined or expressed as a fraction of the collector current. So our base current IB is usually written as IC over a parameter beta. So this would be then IS over beta times EXP of VBE over VT. And from this, we can see that beta is IC over, that shouldn't be a beta, that should be a capital B, excuse me. Beta is known as the common emitter current gain and is a parameter that is highly dependent on the width of the depletion region, the width of the base region, as well as the dopant concentrations of the emitter region and the base region. In a data sheet, you typically won't see beta, you'll see HFE. It is the exact same thing as beta. Okay. So let me write this as A, K, A, H subscript FE, which is what you'll see in data sheets. Typical values for beta range from somewhere in the ballpark of 10 to somewhere in the ballpark of 1,000. So we'll use like 100 in this class as kind of a middle of the road beta for things. Okay. So if we apply Kirchhoff's current law, we can see pretty easily that we have a collector current flowing in, a base current flowing in, and an emitter current flowing out. So IB plus IC needs to be equal to IE. So let's math this up slightly. As soon as the screen decides to stop being a jerk. So we have IS times EXP of VBE over VT plus IS over beta EXP of VBE over VT comes out to be beta plus 1 over beta times IS EXP VBE over VT. In some instances, an alternative transistor parameter alpha can also be used, where alpha is the common base current gain, and alpha is defined as the ratio of IC to IE, or beta over beta plus 1. So usually alpha is a number that is very close to 1, but it will always be slightly less than 1. And so we can then summarize these relationships as our collector current, which is going to be our kind of main current that we're dealing with, is IS times EXP of VBE over VT. Our base current, IB, is 1 over beta times IS EXP of VBE over VT. Or in terms of alpha, 1 minus alpha over alpha, IS times EXP VBE over VT. And then our emitter current, IE, is beta plus 1 over beta IS EXP VBE over VT, or in terms of alpha, 1 over alpha IS EXP VBE over VT. Oh my goodness, the allergies are bothering me so much. All right, so before we move along to look at a large signal model and all that kind of stuff for the NPN BJT, let's work a quick numerical example. So let's say that in a given circuit, an NPN BJT is biased such that it carries a base current of IB is equal to 20 microamps. an emitter current of IE is equal to 1.5 milliamps. And a base emitter voltage of VBE is equal to 0.8 volts. I want us to find alpha, beta, diodes. So realistically, there are two ways that we can go about this. We can solve for alpha first and use that to solve for beta. We can solve for beta first and use that to solve for alpha. And then once we know either of those two quantities, we can then solve for IS. So do you want to solve for alpha first or beta first? Beta? All right. So we know that IE is equal to beta plus 1 over beta times IC. So we'll have beta plus 1 over beta. Well, IC is related to IB as beta times IB. This beta cancels this beta. And so we're left with IE is equal to beta IB plus IB. Rearranging this slightly, we find then that beta is IE minus IB over IB, which comes out to be about 70. Alpha is beta over beta plus 1. So that's 74 over 75, or 0.987. And then from here, we could say that IS is simply IC over the exponential of VBE over VT. So we could say that that is the same as beta times IB over the exponential of VBE over VT, which comes out to be 6.417 times 10 to the negative 17 amperes. All right. So now let's talk about our equivalent circuit large signal models. Actually, large signal All right, so I want to preface this by saying that realistically, once we get comfortable, we're never actually going to use these. This is just something that's in literally every textbook that I've looked at, but in practice, we don't really use them a whole hell of a lot. Okay? So in our analysis of the forward active mode of operation for an NPN BGT, we observed two important characteristics. The forward biased base emitter junction behaves like a diode, meaning that the voltage VBE lowers the barrier potential and allows diffusion of charge carriers to occur from the emitter into the base region. So we have some diode-like control there. And then we also found out that our collector current depends on the base emitter voltage as well. So putting those two things together, we have the following models. So over here on the left, we are going to have the voltage controlled current source model. So this is our base terminal. Between the base and the emitter, which will be at the bottom, we're going to put a diode. And this voltage drop VBE is important. Down here is our emitter terminal. And then over here on the right-hand side, we are going to use a voltage-controlled current source, where this current is IS times EXP of VBE over VT. This is our collector node. Here is our base current, IB, our collector current, IC, and our emitter current, IE. So this is the voltage controlled current source model. And then I'm putting a line here, and I'm going to try to squeeze in the other model to the right. Effectively, it's going to be the exact same thing, except that we're going to use a current-controlled current source, because we can think of the device as being controlled by either the voltage VBE or our base current IB. And this model on the right is then obviously the current-controlled current source model. All right, so the last thing that we're going to do today before I go rinse my nose out is work an example problem. So let's say that we have the following circuit. We're going to have a 2-volt supply voltage. And then I'm going to have a resistor RC that is 500 ohms. .8 volt source here. And we are told the following information. IS is 5 times 10 to the negative 17 amps. Beta is equal to 100. And we want to determine IC, IB, IE, and V out. So I'm just going to label those currents, IC, IE, and IB like so. So which of our two equivalent circuit models, since this is the first time dealing with this stuff, do you guys think we should use? So somebody suggested the current controlled current source model, and I emphatically disagree. So let's talk about why I emphatically disagree. Do we know IB? Nope. Since we know what VBE is, I would argue that using this model is going to make our life easier because practically everything is already known. So that's why I'm going to choose to use the voltage controlled current source model. It is that binary of a decision. What piece of information do I know? Use the one that uses that. So my equivalent circuit for this guy, again, we won't be actually using this for particularly long, is going to look something like this. So here's my base. Here's my diode across which a voltage VBE occurs. Down here is my emitter terminal. Here's my current IS times the exponential of VBE over VT. So let's see, that's my collector. All right, so between the base and ground, I have a 0.8 volt source. My emitter is at ground. Between the collector and the positive polarity terminal of my 2-volt supply, I have my 500 ohm resistor. There's my 2-volt supply. And the negative polarity terminal of the 2-volt supply is assumed to be at ground as well. So, and I'm going to do this in orange because it's weird. There's my output voltage measured. Positive polarity terminal is at the collector terminal. Negative polarity terminal is at ground, which agrees with what we have up here. Okay. So, yes, 0.8. And it should have been 0.8 in both, so let me write it more clearly. Is it clearer that it's 0.8 now? Okay, sorry for my lack of penmanship. I haven't written anything down in 2 weeks. So it looks real shitty, or shittier than usual. All right. So hopefully figuring out what all of our currents are is going to be a joke right now because we don't even need the model for that literally at all. We have an equation, right? Our collector current is literally just IS times EXP of VBE over VT. We know what IS is, we know what VBE is. Let's assume that VT is 26 millivolts because they're operating at room temperature, right? So IC is going to be 5 times 10 to the negative 17 amps times EXP of 0.8 volts over 0.026 volts comes out to be 1.153 milliamps. Using this, IB is just IC over beta. So that's 1.153 milliamps divided by 100 is 11.531 microamps. IE is IB plus IC. So just adding those results together, I get 1.165 milliamps. So no analysis required literally at all. All right, so what's the out going to be? So 2 volts minus 500 IC. Okay. Seems legit to me. So putting in our numbers there, we wind up getting 1.423 volts. Yay, we analyze the circuit. Like I said, the model is pretty pointless for things like this. And even when we get into our larger biasing networks and all of that kind of stuff, the model is still pretty much pointless, which is why I just don't really use it for anything. But here you see it in all of its completely irrelevant glory. All right, so let me ask you guys a question. Is the value of this 500 ohm resistor here important? Could we put any resistor there and expect our device to continue to operate in the forward active region? No, I wouldn't have asked you if the answer was yes, probably. So as long as this base emitter junction is forward biased, our device is going to be on. So the question is, as long as we maintain this 0.8 volts, which we have a voltage source doing so, our only 2 options for operation are going to be forward active region or the saturation region, right? So I would argue that we just proved that this device is operating in the forward active region. And I say that because we can see by inspection that VBE is 0.8 volts and VCE, which is the same thing as V out, is 1.423 volts. So VCE was greater than VBE and VBE was greater than 0. So this device was operating in the forward active region. What if we wanted to figure out what size resistor would put us at the edge of saturation region? Meaning, what's the limit on the resistor that we can choose here before we accidentally push this guy into saturation? Meaning, like this is a practical problem that we might face because we're trying to design the bias network for an amplifier, and we don't want to accidentally push it into saturation because it amplifies less efficiently in that region. Okay? So because we're 1 minute away from the end of class, we'll pick this up at the beginning of our next class, but this is what I want you to be thinking about, I guess, before we go into our next class. All right, hope you guys had a, I don't know, less than miserable time in class today. Yes. We're still on track. Yes. Yep, test is on Friday. This is not on the test. Everything else we did is. All right.